times. I think it may have happened here a couple of times. It's happened in California. So it's kind of a consistent thing that you're in the port facilities, you have saturated soils, they're often sandy. Once you have liquefaction, you can get problems. And that's really not what I'll be focusing on today, the liquefaction problem. Another case where you see failures of retaining walls is unreinforced masonry walls, which literally just topple over if the shaking is strong enough. This is from an old masonry wall in Italy from the 2009 earthquake, L'Aquila earthquake, and there are many other such examples. So there are these exceptions, but the overwhelming majority of cases, things do well. And despite the fact that these walls do well, we have guidelines that sort of force us to do seismic design for walls, even though some of these walls that do well were never designed for earthquake in the first place. But I think it's sensible that we know that the earthquake must do something in terms of applying pressure on the wall, and we as engineers should account for that. And as a result, we do have different guidelines documents. We can't be driven entirely by observation, right? We have to go back to first principles. And first principles tell us there should be seismic pressures. The guidelines reflect that. So there's the Building Seismic Safety Council, that's the NEHR provisions, talks about seismic earth pressures, as does this highway manual, NCHRP. Notice that the NEHR provisions document I'm citing here is from 2009. So that is in reference to a previous version of the seismic earth pressure guidelines. There's some newer ones published in 2020. So with these guidelines documents for seismic earth pressures, there's basically two ways that are mentioned that you can do it. The first way is you can do a very thorough, we call this a direct analysis of a soil structure interaction problem. And let me see if the pointer's working. Yes, well maybe this pointer's a little bit stronger. Better. Okay. So what we're looking at here, this is a wall. There's actually a structure attached inside. These are the soil elements around it. You have some kind of transmitting boundaries out here, and then you have a three-dimensional wave field that's coming in to this system. And so if you analyze this complete soil structure interaction system, there will naturally be pressures that develop against the wall, and that's a direct analysis. So that's one way of doing it, and the guidelines reference those things. They don't get very specific about how exactly to do these soil structure interaction analyses, but they basically give permission to compute earth pressures that way. This isn't done very often, as you might imagine. It's very expensive, but it is done for some projects. So major, like one example would be a major transit station that is below ground in an urbanized area. You'll do these kinds of analyses for those structures. If it's a retaining wall for somebody's house, probably not going to do it. So at some point, you go from simplified to more complicated, and it's really driven by project budget. What's mostly done is these so-called limit state analyses, and I'm going to try to explain them here. So this is the wall, this is the retained soil, and in the limit state analyses, you have an active wedge that's assumed behind the wall. When there's no earthquake, this KH would be 0. You would just have the weight of the wedge, the reaction force, and you would have the active earth pressure resultant. When the earthquake comes, you have a pseudostatic force applied here, which is some fraction of the weight. That's going to likely change the position of this wedge, and you're going to have to re-resolve all of these forces, and you'll have a new increment of force, which is called P sub E. Okay, and so this P sub E is what we're going to be looking at today. If we just look at the force polygon, you can see that if this is the weight and this is a reaction, the action of the earthquake is to lengthen the force vector of the soil against the wall or the wall against the soil. You can tell because this is moving over. So the P sub E is always an additive pressure in this framework. So I mentioned that we've been doing it a certain way for almost 100 years, and that certain way goes back to some experiments that were run in Japan in the 1920s, so-called Mononobe Okabe methods. And one sort of relatively recent publication using these methods was from Koseki et al. 1998, which is what I'll reference here. So they take this combined force that I was just talking about, they normalize it in this way, so it becomes dimensionless, and that is KAE. So Koseki et al. Present KAE, a dimensionless number, as a function of the horizontal seismic coefficient. And these different lines here are for different friction angles of the soil. And there's a number of geometric variables defined here, which are given down here. It's the angle of the backfill, the angle of the wall to vertical, and so on. So if we were to come in here, for example, at 0.5 G, you can get numbers of 0.4 to, say, 0.9 or so as the horizontal pseudo force. That's a pretty strong one. Seed and Whitman came up with an approximation of this rather complicated relationship where they said, well, the delta, that is the seismic increment of this KAE, can be approximated as 0.75 times KH as long as KH is less than 0.4. So that's this red line. And the reason they did this is something that you can see in this plot. If you follow these lines, look what happens when you get to large ground motions. They go vertical, which means you're getting to infinite force, basically. It becomes an unstable calculation. And part of what Seed and Whitman were trying to do was make the calculation simpler, but also to have something that would be more numerically stable for use in engineering design. Okay, so this leads us now to what do we actually observe? This is the kind of theoretical framework that we've been working with for many, many years. It's a force on a wedge. Okay, so that's how we represent the seismic earth pressure. Let's look at what actually happens, and then we're going to see if this methodology that's been used for so long makes sense. So there's quite a few tests that have been run. I'm going to show you some representative ones here. So we, as far as I know, we don't have any field case histories with an instrumented wall that has recorded pressures under design level earthquake shaking conditions. So we don't have that. What we do have is centrifuge tests. And I'll be showing you these centrifuge tests done at UC Davis by Nick Sitar and a number of his students over the years. There's also some tests run at CU Boulder by Shade Dashti and her students. And I'll make reference to those at the end, but in the interest of time, I won't show you the details of their setup. It's similar to the UC Davis one. And then there's a number of dynamic analyses, essentially direct analysis, where we can calculate what the pressure was. So we have different kinds of observations, measured ones in centrifuge tests, calculated ones from direct analyses. So this is the first big centrifuge test. This was really a very impactful study on this topic by, again, Nick Sitar and Linda Alatique at UC Davis. I should say they were at Berkeley, but they were doing the tests at UC Davis. And they tested U-shaped walls, a rigid one and a flexible one. This is centrifuge, so these are prototype units. Once you scale it up for the spin rate of the centrifuge. So this is the wall height, this is the wall half width. And then the key detail of these tests is there's distance between the bottom of the U and the bottom of the model. That's important because this soil here allows the wall to translate if it wants to, it can rock, it can respond in a natural way. That's important to point out because a lot of the theoretical solutions we have, and many of the past experiments also, are on a rigid base. So on a rigid base, the wall can't really move that much. In fact, it can't move at all at its foundation. This is a more realistic setup, so that's a very nice feature of these tests. They ran 3 different time series through it. And here's one of the results. So this is from a motion they were calling Loma Prieta SC2, so that would be from Santa Cruz. And the horizontal axis is the pressure, in English units, PSI. This is the depth below the ground surface. You see these symbols here, so these are essentially point measurements of pressure using these so-called flexi-force sensors. You see stiff and flexible, that just refers to the two different types of walls they were testing. And then these dotted lines here, this SG is strain gauge. So they had strain gauges which essentially measure curvature of the wall, and through some manipulation you can convert the curvature into a force distribution. The way that the calculation was done is you are required to have a linear distribution of force with depth, so that's not really an outcome of the test. It is partly an outcome of the test, but it's an enforced condition in the way they converted the curvature into pressure. Okay, so you have the two dotted lines here. You have the individual measurements from FlexiForce, and so you can pretty much see what the pattern of earth pressure with depth was from this earthquake. Also shown here is the so-called Mononobe Okabe, so that's that limit state method where you take the seismic coefficient as the PGA, okay? And what you can see is that this is bigger than that. So then they said, well, since the PGA isn't working, let's use 65% of the PGA. If you've studied geotechnical earthquake engineering very much, you kind of know 0.65 is a magic number. And so we multiply by 0.65 and voila, it works great. Okay, so we can, maybe if this is the way it is, we can just use 0.65 of the PGA. Thankfully, they ran more than one ground motion. So this second ground motion from Kocaeli, Turkey, same format as the one over here. Here's the full PGA, here's 65%. 65% is now too much. So if you wanted to match the data for the Kocaeli ground motion, maybe you would need to use 50% or some other number. What you find if you look at many of these things is essentially every ground motion needs a different factor. There isn't a unique factor that's going to cause the theory to match the data, which suggests that there may be a problem here. So the main takeaways are the total earth pressures that we see in these tests are consistently below Mononobe Okabe. The other tests at Boulder and the other tests that Nick Sitar did with subsequent students all showed that, so it's very consistent. The Mononobe always predicts, but one of the most recent recommendations is, well, if you take a depth averaged PGA instead of the PGA at the surface, maybe that does a better job. So that's trying to come up with something that is customized for each ground motion. Okay, so again, let's keep in mind that when we look at tests, the limit state methods overpredict. We can try to put a Band-Aid on it and fix it in different ways, but they tend to overpredict in just their natural state. This is dynamic analysis. This is essentially direct analysis for a rather simplified set of conditions. You have a rigid base, you have a rigid wall, and then you have elastic soil. Many different investigators have considered this situation. I'm going to look at one set of results from Farhang Özdağ, who's an engineer at Bechtel and has done a lot of work like this for the nuclear industry. So this is the conditions I described. The input motion is broadband. That just means it's a motion that has energy across a wide range of frequencies, like a real earthquake would have. There is a very strong site response if you have rigid base and elastic soil. There's nothing to damp out the energy, and you have an infinite impedance contrast, so you're going to get a big site response in this condition. So this is some of Farhang's results here. Kind of walk you through it. This is the wall heights. This would be the bottom of the wall. That would be the ground surface. These are pressures. The Mononobe Okabe prediction, I should say, is this one. And these different colored lines are different ground motions that he ran through his calculations. The important point isn't any one of these motions, but it's the fact that these are bigger than that. Remember that we had exactly the opposite from the experiments. So if we summarize these observations, we see that the centrifuge tests are giving us pressures lower than Mononobe Okabe. These analyses for these conditions, elastic soil and so on, are giving us pressures bigger than Mauna Obi-Okabi. So these two sets of studies, the study on the UC Davis centrifuge and this particular paper by Ostadon, were done in the context of work that was happening at that time on BART tunnels. BART is the transit system in the Bay Area. And there was a very heated debate going on. You're wrong, no, you're wrong. Which one should we believe? What's going on here? So there's a lot of confusion. The one thing that everybody could agree on at this time was that Mauna Obi-Okabi seems to be wrong, but is it wrong in an unconservative way, or is it wrong in a conservative way? Which leads us to the new relatively disruptive framework, which is looking at this from a soil structure interaction perspective. And there's a lot of stuff that's going to follow here now, but there's one most critical point that I'm going to tell you right now, and I'm going to tell you it again a bunch of times in the next few minutes. And that is, what is it that actually causes pressures to develop against a wall? When you get right down to it, there's a very simple principle that's at play here. If the soil and the wall are moving differently from each other, you're going to get pressure. If the wall and the soil, imagine this hand is soil and this hand is wall, imagine they're not moving relative to each other. You can put your hands together and translate them back and forth, and the pressure between your fingers doesn't change. But now if you start pushing on one side relative to the other, this one's displacing differently, now you feel the pressure between your fingers changing. That's really all there is to it. So how can we take this relative displacement principle and make it actionable, make it usable? So when we talk about SSI principles to this problem, it's this. This is all there is. Now there's a lot of factors that influence the relative displacement, and you'll see what those are. But the core principle is actually very simple, and it's hard to argue against this. You need relative displacement. Think about a spring. When does a spring force change? It's when you deflect it, right? You have to have that in order to get a force change or a pressure change. That's all we're saying. So I'm going to start with the inertial part of this. Certainly, there is potential for wall pressures to develop under the inertial situation. So if we think about a structure here, I'm just showing part of it. This is a cutoff. Here's a building structure. This building, when it's responding during an earthquake, is going to develop inertia, and that's going to translate into a base shear force and a base moment. So you're going to have shear forces coming in at the foundation and moment that's going to be causing overturning. If this foundation's on a rigid base, then the foundation doesn't react. It just, that force immediately goes into the rigid ground. But of course the ground isn't rigid, right? And so that force must be accommodated through deflection of soil springs, or more realistically, the soil as a whole. But in this idealization, the soil springs. Rotation will accommodate the moment. So this foundation in reality is displacing relative to the free field, and it's rotating because of the base shear and the moment that's created by inertia. So if you have walls connected to a structure, there will be this inertial component, okay? And the key issue that an engineer needs to think about is how connected is the structure to the wall? Is there a structural connection between the two? Then the transfer happens. Sometimes there isn't a structural connection between the two. It all depends on the configuration, so we need to look at it case by case. Okay, so this is just to highlight that point. We need to think about, will the load path coming down from the structure to the foundation pass through walls, or will they not, if you want to look at these inertial pressures? I'm going to give you two examples. So the case we just looked at, clearly these structural elements are connected to these walls, so there's no ambiguity here. Those walls will be participating in transferring load into the soil, and inertia will be probably the dominant source of pressure in this case. This is a very common situation with tall buildings in California, maybe here in Mexico too, where if you have a tall building, you will often have a shear wall near the middle of it, which is the principal carrier of lateral loads. And that shear wall doesn't stop at the ground line. It goes all the way down to the foundation. So you have a continuous load path down to the foundation. When you get below the ground line, so this is the ground line here, right? You often have these widened structures that can be for parking, it can be for retail space. That's called podiums in construction. And these broader podium structures may or may not actually be connected to the tower. So there's some important structural details I'm not really dwelling on here, but this podium, which could be much bigger than what I'm depicting in the schematic, may or may not be connected. If it's not connected, then these walls really don't have an inertial component. It becomes a kinematic problem. On the other hand, if there is load transfer, say through this diaphragm, then again there would be inertial contributions to those wall pressures. So how can we analyze these things? Well, we can always do direct analysis. I mean, this pretty much always works. So you're never going to go wrong if you do these numerical calculations and you do them correctly. But as I said, they're very expensive and we can't always do it. On the more simplified side, we can use these spring-type representations of the soil. We put in the free field ground motion at the end of the springs, we work it out, and you will get pressures that develop. So either way, the more complex one or the simplified procedure, which is sort of codified in these NIST documents, will naturally give you the seismic pressures from the inertial component. And so as we started to think through this SSI earth pressure problem, we didn't spend too much time on the inertial part, even though it is important for many cases, because the means by which to analyze this problem are already pretty well developed. So that's the last I'll say about inertial here today. And we'll focus going forward on the kinematic part of the problem. So what do I mean by kinematic? So when we talk about kinematic soil structure interaction, and it has many different manifestations, the one common thread in a kinematic soil structure interaction is there's no inertia. You're sort of idealizing the problem as massless, and you're looking at contrasts and stiffness and things like that and what it does. So this would be a kinematic problem. You have only the foundation and the soil around it. You have a free field motion over here. So this is a motion, by definition, not influenced by the structure. That's why we call it free field. The free field motion at the ground surface, we denote UG naught, and it of course varies with depth. It more or less follows a cosine wave pattern for a given frequency. Okay, so the classical kinematic problem is how does this motion at the free field compare to this motion in the foundation? And there's been lots of studies that show they're different. The foundation input motion is smaller for various reasons. But you will also tend to get wall pressures that develop if this motion and this motion are very different. Okay, so let's explore that going forward. So I'm going to walk you through a series of kind of conceptual drawings here to help us understand what produces pressures under kinematic conditions and what doesn't. So here we're looking at an element of soil with a vertical and a horizontal stress before the earthquake comes along. Now we have an earthquake. It produces sort of this typical cosine wave type displacement pattern. At a particular point in time, you have an acceleration at the ground surface. If we look at the soil element, if you've had a geotechnical earthquake engineering or soil dynamics course, you know that the soil element, when you have a free field motion, is going to develop a shear stress. So the inertia of what is above that element is accommodated by the development of this shear stress, which is the same on the horizontal and vertical planes. That's important. The inertia is actually completely handled by the change in shear. There is no change in the vertical stress, and there is no change in the horizontal stress. Of course, I'm not considering liquefaction and those kind of things that would change effective stresses. If we leave that aside, say there's no pore pressure development, everything is handled here in the form of the shear stress. Okay, so now let's look at an inclusion within the soil. And our soil element is right at the edge of that inclusion. But I'm being a little bit tricky here. My inclusion has the same mass, so mass density and stiffness properties of the soil. So just because I put this inclusion in there is not going to make any difference. I'm going to get exactly the same pressures. The only thing that matters in the response is the stiffness and the mass properties. Conclusion or not, it doesn't make any difference. Okay, so now let's go to a more realistic case where the inclusion is very stiff, in this case rigid, and now we put that wave through there. So what's going to happen now is you still have this free field motion over here, but this rigid inclusion cannot deform in the way that the free field soil would like it to. It's just going to rock a little bit, it's going to translate, but it can't have any shear or bending deformation because it's rigid. As a consequence, things change around that inclusion. This motion now is different than that motion, and while you have shear stresses here still, they'll be different than they were before, and you will now develop changes in the horizontal stress and changes in the vertical as well. Now we're looking at seismic earth pressure, okay? So the key point of these schematics is basically to explain that seismic earth pressures are fundamentally related to the relative displacement, the difference between the displacement of that inclusion and the free field. And they are not related, equally important, they are not related to this acceleration. Remember, before the inclusion was rigid, we had acceleration, but we had no pressure. Acceleration, no pressure. Now we have acceleration, and we do have pressure. So what's the difference? Relative displacement. There is no fundamental relationship between acceleration and earth pressure. That's an important thing because remember, Monobiokabi is all about an acceleration causing earth pressure. That is the independent variable that drives the earth pressure. So you can see the problem. So how can we do kinematic modeling? Well, we can always do direct. That'll be a natural outcome. If you had a kinematic version of this, you would simply have no structure, okay? So you can do that. But we're going to focus on the simplified methods, and this is what we've been developing over the last few years. I'm going to go through the simplified methods in several stages. I'll focus mostly on the first and the third stage, but we have a basic case which helps us to understand some of the physics. In this basic case, we simplify the problem quite a bit in order to have closed form solutions. So we're going to have a rigid wall, so that means infinite bending stiffness. The soil is uniform, it doesn't increase with stiffness with depth, and there's no inertia in the problem, so it's a pure kinematic problem. So the reason these simplifying assumptions were made, it allows closed form solutions to be developed. This was published in a paper in 2015, I'll have the reference later, and it's very useful to have this closed form solution. It reveals one of the most critical factors that drive these earth pressures. But we recognize there's problems with these assumptions. They're not very realistic, so there's a more complete model where the wall is flexible, the foundation itself is flexible, it can have its own distortions, the soil can become non-uniform, and inertia is allowed into the system. This is not amenable to a closed form solution. Now you need to go to a numerical solution. And so that was done, and that would be paper number 2. And what that solution basically will give you is a time for a given input motion and a given set of properties of soil and wall, you'll get a time series of that PE force. That's too complicated for most engineering problems. Keep in mind that our competition, if I can put quotes around competition, in developing this is Monobiokabi, which is, for all its faults, it is easy to use. All you need is a PGA and a friction angle, basically. So we need to come up with something similar in level of difficulty. So we need a single frequency or a simplified model, and that'll be the third paper. So as I go through this, I'll be focusing mainly on this first one and the third one with just a few brief remarks on the middle one. So this basic case, that first solution, we have in the free field certain attributes of the waves, which are depicted here actually. So there's a wavelength of the wave and there's the free field displacement UG naught. So that's essentially what this red line is here. So I have a free field displacement, which is UG naught cosine 2 pi z over the wavelength lambda. C is the depth below the ground surface. The same basic setup applies for U-shaped walls or just a single cantilever wall like this. As I said, we have a rigid wall and a foundation, so The reason that this assumption was made is that if it's rigid, you can describe the displacement of every point along this wall just knowing two things. The motion at the bottom, the UFIM, this one, and the rotation. If I know those two, I can calculate the displacement of the wall at any height. Okay, so now we get to something that's maybe a little unfamiliar to most of you, I suspect, is that this notion of a stiffness intensity. As engineers, we all understand what a spring stiffness is. Stiffness intensity is just a variation off of spring stiffness that is more convenient for this problem. I'll explain that more in the next slide. The stiffness intensity, actually before I go on from that, is essentially describing the stiffness of these springs between the wall and the soil. There's a horizontal one and a vertical one. Horizontal is KY, the vertical one is KZ. Essentially, the stiffness intensity is a stiffness divided by area, such that this particular spring would be the stiffness intensity times the tributary area for that spring. Okay, so what we're doing to solve this is we, for a given displacement here, we're going to get some deflections of the springs. These spring forces produce shear and moment, and that shear and moment has to be balanced by the shear from the space spring and the moment from this rotational spring. And so you can set up a series of equations for the horizontal and the rotational vibrations, and you can use those to solve for the foundation input motion and the theta, and this solution is for one frequency, and then you can work it through for all the other frequencies. Once you have those displacements, you know the displacement of the wall, you know the displacement of the soil, now you can get the relatives and you can work out what the PE force is. All right, now just a bit more about the stiffness intensities. So here's our wall. Here again is the force coming in from a spring, and we need this horizontal, obviously, and the force from that spring is the KYI, the intensity times the area that's tributary to that spring. The I here is to indicate intensity, and the units are force per unit length cubed. Remember that stiffness generally is force per unit length, so it's basically stiffness divided by area. The equations for this are worked out in our papers. They're basically showing that these intensities are proportional to the shear modulus of the soil. So there's a couple different solutions with the references there. The other thing I've shown at the bottom here is why we need the vertical. So if I go back for a minute and you follow this, this is the unrotated foundation. This is the rotated one, and you can see that the rotated foundation is moving down on this side and up on that side. So as it moves down, the soil will resist that. You'll get this shear force, which is KZI times dA. So we need both the horizontal and the vertical for this problem. So if you work out the solution and you express the results in terms of the pressures, there are also solutions for the displacements, of course, the UFIM and so on. You get this. This is a very important figure in the presentation. So what we're looking at on the vertical scale is this normalized force, the earthquake resultant, which is in units of force, divided by UG naught. That's the free field displacement at the ground surface. KYI is the soil stiffness, and H is the wall height. This is dimensionless quantity. The horizontal axis is the wavelength of the wave divided by the height of the wall, also dimensionless quantity. So if we look here, we see that there's this very strong dependence of the normalized force on the wavelength. This relationship peaks at about 2.3 wavelength to height ratio, and it becomes very small as the wavelength gets large. There are closed form exclusions for this expression, for this plot here, which is written out here. So the dimensionless force is a function of kh, where k is the wave number as given here. The bottom figure is essentially the resultant height. You can see it doesn't vary all that much with wavelength. The reason you need this height is to calculate moment. So the force times the height would give you the moment at the base of the wall. So the critical finding here, remember it's all about relative displacement, But one of the things that really drives relative displacement is wavelength, okay? And in the next couple of slides, I'm going to try to show you why wavelength matters so much. So here we have a wall. Here we have a long wavelength, which goes with a low frequency. So long wavelength, frequency small. If that's small, that's large. And if that's the case, you can just see here with your own eyes that the displacement of the free field doesn't vary that much over the height of the wall. So the UFIM and the UG naught are going to be very similar. There won't be much rotation. The theta won't be much, and so there's really very little kinematic response of the wall under these long wavelengths. So there's small relative displacements and there's negligible pressures. Just to be clear, it's not that the wall system isn't moving. It absolutely is moving. It's going back and forth. It's just that it's going back and forth in the same way that the soil is. So the relative displacement is very small. A high frequency, so if that becomes large, the wavelength becomes small. So you see this small wavelength, now there's a lot of displacement change over the height of the wall. This motion will become very different than that one, a lot smaller. The different levels of force here are going to introduce rotation, so you're going to have rotation, lots of relative displacement, and you're going to get a lot of wall pressure. So it's as the wavelength gets small relative to the wall height that you develop the pressures. That's essentially what the previous plot showed. Okay, so that's that simple model. The more complete model, we have the flexible wall and all these other conditions that are accounted for, and I'll just talk about mainly the flexible wall part of this, because we've investigated all these effects to see which are the ones that are most impactful, and wall flexibility is the big one here. To work this out requires a numerical solution of the equations of motion. There is a full frequency domain solution. You give it an input motion, and you get a time series of the wall responses and the reaction forces. It's implemented in a Jupyter notebook, which is published. Anybody can go get it and try it out. It has a nice interface, and you're welcome to give it a try. The key variable that comes in with this solution is wall flexibility. And the wall flexibility has a parameter that describes it. This is kind of a classical parameter in soil structure interaction literature, beta. Unlike most variables in soil structure interaction, beta is not actually dimensionless. It has units of 1 over length. It's basically KYI divided by the moment stiffness of the wall section. So the EI, that's the moment stiffness of the wall section. Here's just an expression for it that depends on the thickness of the wall, the Young's modulus of the wall, and its Poisson's ratio. So the way that we make this dimensionless is we multiply beta times the wall height. So 1 over length times length becomes dimensionless. And it turns out that if this product is less than 0.5, effectively your wall is rigid. So if you use that in the solutions, you end up going back to the rigid solution. So what we did when we started thinking about this wall flexibility is we consulted practicing geotechnical engineers in Los Angeles who had designed walls recently for major structures, including subway station structures and tall buildings, and we got the plans and cross sections for their walls. And we calculated beta times H a bunch of times. And we found that the typical values that they're coming up with are more like 1 to 3. So as the number increases beyond 0.5, larger numbers here are indicating greater flexibility. The way to think of it is if you make this smaller, the wall becomes more flexible, beta goes up, and therefore beta times H goes up. So in the same form as the previous solution that was rigid only, now we're showing what happens as you go to these different values of beta H. And what happens is that the wall resultant forces are dropping, and these drops are not inconsequential. These are pretty major impacts. The wavelength effect is still there, but now that we have the second effect of wall flexibility, which is very important. Okay, so that's the effect. Now to dig a little deeper into this wall flexibility, why is it having such an influence? This is showing the displacement of the wall divided by the free field displacement as a function of height. So this would be ground surface, this would be the base of the wall, so h is the wall height. And you have different beta h's here. Actually, the soil displacement is here as well. This is the soil displacement, not the wall. And all these other colors here are the wall displacements. And they're for different beta h's. So 0.5 back here, not much wall displacement. And the key thing to look at is the difference between the wall and the soil. So you have a big difference there that drives a big pressure. Now if we go to beta h of 2, this one's over here, there's still a displacement, but it's much smaller. So you can see that by allowing the wall to have flexural flexibility, it's more able to conform with what the soil wants to do, and you don't have as much relative displacement. So those are displacements. These are the actual pressures in a dimensionless form, and you can see what I was just talking about. So the beta h 0.5, which is practically rigid, has large pressures, and it drops as beta h goes up. Okay, so this leads us to the single frequency model, where we tried to pull all this stuff together, have a simple method that accounts for the most important effects, doesn't account for every effect. Intentionally, we leave some out to make it simple. So that introduces some potential errors. I'm going to walk you through how you would do this. So as the method's name implies, we simplify it in one way because we say, well, this complex time series, we're going to just simplify it to a single frequency. We're not going to use ground motion as a function of time. We're going to use an intensity measure that goes with that single frequency. So there's no more Fourier series, there's no more time series. We're going to consider in this the wavelength, particularly lambda over h, and we're going to consider beta h, basically. We've considered all other factors in the development and found that they weren't that important compared to these. So the approximations, we neglect inertia. We do use a homogeneous soil. We use linear properties for the retained soil, and we use a fixed space. Of these approximations, the one that probably should stand out to you if you're a geotechnical earthquake engineer and you've studied nonlinear behavior is, why in the world would these guys have a linear model? Okay, in general, it's pretty broadly accepted in every seismically active area around the world that soil is nonlinear. This is not a debated point in geotechnical earthquake engineering. It's a point that I am very well aware of. So why would I write a paper that I recommend for practice in which we have a linear model? So instead of making a complicated series of plots, I'm just going to point out that there's two counteracting effects when you go from linear to nonlinear. When you go from linear to nonlinear, you make the wavelength shorter. When you make the wavelength shorter, you get more wall pressure. When you go from linear to nonlinear, you make the G smaller. The stiffness goes down. That makes the stiffness intensity smaller. These counteract each other. Not perfectly, but when you actually run through different cases, you find that the change that you get by going to nonlinear, pretty small, and it makes the analysis a lot more complicated to deal with it. So this is why we went with linear in the interest of simplicity, but also because it actually works pretty well due to these counteracting effects. Okay, so now here's the procedure. You do a seismic hazard analysis. The ground motion parameter we want is PGV, velocity. The reason we want PGV is it's an intensity measure that measures kind of the center of the frequency range of most ground motions, and that's the part of the ground motion that is most likely to produce these relative displacements. Once we do a seismic hazard analysis, we do a deaggregation, we get a magnitude and a distance that go with that PGV, and then we use empirical relationships to get a central period that goes with that magnitude and distance. We call that TM. One such relationship was published by Ellen Rathje and her colleagues, which is shown here. So for example, at 50 kilometers for a soil site, you'll have something like 0.7 seconds mean period. Now you need to have a shear wave velocity profile. You either measure it, or if the wall isn't built yet, you can't measure it, but you can estimate it. It's not that hard to estimate the shear wave velocity of sand, if you know the relative density you're going to have. So you have you have a shear wave velocity that varies with depth, And you really need to know those shear wave velocities over the height of the wall. And we're going to take an average velocity, which is essentially a time average velocity over the wall height. So it's the wall height divided by the travel time over the wall height. The same calculation we do for VS30, just now it's wall height instead of 30 meters. So now we have a VS, we have a ground motion, we have a period. We're going to now estimate the displacement that goes into these calculations as PGV, which has units of velocity. If you divide it by omega, that converts it to units of displacement. So this would be kind of the theoretical displacement for a sinusoid. This factor FU was worked out in order to essentially match these single frequency solutions to broadband solutions, and it varies from 2/3 to 1 depending on lambda over h. Okay, now we have our stiffness intensity. The stiffness intensity equations in literature are frequency dependent. We've simplified them to frequency of 0 solutions, again, to make it easier to use. You need Poisson's ratio, the shear wave velocity we calculated before, and the wall height, also the mass density. The Poisson's ratio for sand's about 0.3, so really this, you just need the shear wave velocity for this step. Now we get we do a section analysis to get beta. Now many times, at least in US practice, geotechnical engineers are working out seismic pressures before the structural design has been done. So there's actually no way that you can come up with this on your own. And for that case, we say, well, if you really don't know, a conservative estimate of this would be in the range of 1 to 2. You're not going all the way to rigid, but that's kind of at the low end of what we see in real walls. Okay, so now you have everything you need to use these solutions that I've been describing for you. The horizontal axis, in terms of the variables that we've just defined, is Vs times T divided by H. And we don't really need to use these plots directly. We've converted them into a normalized force, just representing this change as beta over H goes up. So we have an equation for this, and this is the corresponding change in the wall height given beta over H. And so there are equations for those two curves, and you basically modify what you get from that simplified solution, those closed form expressions I showed before with this, and you have your result. And this is the way it is. So this is that simplified solution for rigid, and you basically are modifying it through this factor here, and this is the equations I just mentioned. You denormalize that force, so it is normalized, so you see that what we're calculating is this ratio, so we multiply by this, this, and this to get the actual force. All of those have been determined in previous steps, and then the force times the height of the resultant gives you the moment at the base of the wall. Okay, so the last thing I'm going to do is describe validation. Does this actually work? And so we validated it using the UC Davis tests, the Colorado Boulder tests, and the theoretical solutions. So what I'm showing here is the normalized force, lambda over H. You see this gray zone is representing the range of beta over H for all these experiments and simulations. The red symbols are the Boulder tests. The blue symbols are the Davis tests. The green symbols are Ostadon's analyses. You'll notice that generally speaking, there is a decay in these forces as you increase lambda over H, as the theory requires. These are all for relatively flexible systems, these experiments. Remember, Ostadon is rigid, and so you see that Ostadon does lie above these other solutions here. What is helpful in a situation like this, because you have many different beta H's, is to take the beta H for any individual test, run the calculation, and calculate a residual. So you take your measured one, you subtract what you would predict using the method I just described, and that's a residual. We take the difference of the logs. So 0 would mean a perfect prediction. This would mean that we're under-predicting. This would mean that we're over-predicting. So again, red is Colorado Boulder, blue is Berkeley / Davis, green is Ostadon. And you see, of course, this isn't perfect every time, but the trend is pretty good. It's averaging close to zero. It's actually a little bit negative, and that's what these numbers here show. That was intentional, okay? It's averaging a little bit negative, which means we're about 10% conservative. It's a simplified model. It should be conservative. There should be a benefit to doing a more thorough analysis, and you would remove that conservatism. There is some dispersion. So this looks pretty good, but I think to have some context, how well would Mononobe Okabe work if you applied it to these same analyses and experiments? So what you're looking at is the residuals for Mononobe Okabe, where you use the PGA as the seismic coefficient. And for a substantial number of these experiments, there is no solution. The earth pressure goes to infinity, so the residual goes to negative infinity. So that's marked here. But for the ones that you can actually derive a solution, for all these experiments, you have a strongly negative residual, which means we're over-predicting. For Ostadon, like I showed earlier, we under-predict. So the same thing is shown in different ways here. And there is this huge trend with increasing PGA, which is just a feature of the Mononobe Okabe method. It basically becomes unstable for strong ground motions. If you say, well, I don't want to use PGA, I'm going to use 0.65, it does make things better. Fewer don't converge at all. You have still strongly positive, in fact, much more positive here. You have some that are around zero. So it's better, but you still have this strong trend with PGA. You don't want trends with your predictor variables when you have a model. If any one of you was to propose a model where a parameter that goes into the model is PGA, and your model has huge bias as you trend across different PGAs, your paper would be rejected. If your reviewers are actually reading the paper, you will be rejected. You can't do that in a predictive model, and yet this is what we've been doing for 100 years. Okay, so what we have is not perfect, but it removes that trend. And the reason for the difference, of course, is we're accounting for the problem physics. Okay, it's all about relative displacement. It's not about acceleration on a wedge. So I'll summarize now. Seismic earth pressures on walls result from relative displacement. If there's nothing else that you take away from this presentation, I hope it's that. That's actually a general principle for all kinds of soil structure interaction problems. It's all about relative movements. These relative displacements can happen from inertial sources or kinematic. The limit state procedures, which have an active force on a wedge and the active force is related to the acceleration, don't capture either of these mechanisms. The seismic earth pressure increments has no fundamental relationship to PGA, so we shouldn't expect a PGA-based method to work. The SSI procedures are capturing the observations and they're resolving conflicting findings in the literature. So if we go back to this Ostadon debate with Sitar and others, it's not that one was right and one was wrong. They were both right. Both did perfectly fine evaluations of seismic earth pressure. The problem was they were comparing it to something that doesn't have a physical basis. That's why it was high in one case and low in the other. There was nothing wrong with either of their results. This does require separate analyses for inertial and kinematic, but if you have a big inertial thing coming into your wall, you can probably ignore the kinematic, honestly, and just work on the inertial. And if you don't have any inertial, then of course you just have kinematic. So for a lot of problems, you end up just looking at one or the other based on engineering judgment. This single frequency procedure is in a NEHRP Part 3 paper, and it's been published in a journal paper a few months ago as well. Maria Giovanna Durante is first author. So the next steps are implementation. It is being used by different engineers across the country now. In the US, they're trying it out. They're generally finding the earth pressures are going down, so they like that. And I think we're going to see it increasingly be used as time goes on. So these are the references. I talked about the papers 1, 2, 3. So this was 1, this was 2, and this is 3, which is pretty much the same as this NEHRP document. Okay, so that's it. Thanks for your attention. I'm happy to take any questions.
Thank you, Professor John, for your talk. I have a question. This has been compared with practical cases recently?
Well, there's nothing to compare to. They just try it out, right?
With instrumented.
But
yeah.
there's no right answer.
Okay.
If you're just applying it as part of a design process. So the application where you know the answer is the validation that I showed.
Okay, and how does it work with, you mentioned that you consider an homogeneous soil. If we consider an heterogeneous?
Yeah, we have. So we have a paper on that topic, actually.
Okay.
The reason we didn't move that forward into the simplified procedure is it just makes the calculation of these pressures more complicated. It does have an influence, but its influence is really of secondary importance compared to what I talked about. So by doing the time averaging procedure, you do a decent job of capturing that. Now, if you're doing a direct analysis or you're a more complete analysis, you can definitely account for the variations, and it will impact the distribution of pressure over the height of the wall.
Okay, thanks.
Thank you, Professor, for your talk. How does it work, this method with water pressure behind the wall?
So if you have water pressure, are you talking about on the retained soil side or the other side? Well, so this doesn't deal with pore pressures that develop as a result of liquefaction or softening of clays, right? So these are total stress solutions. So when you have strength loss due to pore pressure increase, it actually makes the static earth pressures, those that would be there even if there was no earthquake force, go up considerably. It also reduces the resistance at the foundation. So this is why we see so many problems with that. So this is a total stress solution. It doesn't deal with that problem. The way that I would handle this in practice is I would actually start with the liquefaction problem. That is the more serious problem if you have it. So if you're worried about liquefaction, you should really do that first. And if you think your wall will become unstable as a result of liquefaction, either in the backfill or the foundation, you have to fix that first, either by improving the soil, lowering the groundwater table, or any of the typical ways that we can handle that. And once you get into a regime where you don't expect pore pressure, then I would use something like this.
Thank you. Firstly, thanks for your presentation. It's very interesting. My question is related to, in your research, do you identify more effects related to the height of the wall?
So let me see if I understand. In the course of our research, did we identify effects that maybe I didn't talk about here related to wall height?
Okay.
Is that what your question is?
Yeah, no. Apart from the effects that you talk in your presentation, do you identify more effects, or that's all the effects that you're presenting?
Okay, so are there other things that I haven't told you, basically? Yeah, I mean, in the course of doing work like this, there are all kinds of things you try, before you sort of settle on what you think the key factors are. So one of the things we looked at in considerable detail, we thought it would matter a lot, was the non-uniform soil. We spent a lot of time on the flexibility and shear and moments of the foundation of the wall, which is really important for a rigid wall. It turns out it's not that important once everything becomes flexible. We looked at cases, mostly because it was in some of the experiments, where you have a lid on the top of your U-shaped wall, so there's inertia introduced through the lid. We've looked at nonlinearity. So we've looked at many different things that I didn't actually talk about here today in order to just distill it down to the essence. But if you have interest in this topic and you want to see some of those more nuanced points, there are publications about it.
Okay, thanks.
¿Alguna otra pregunta? I have a question, well, a couple of questions. One is, here in Mexico we have these very deep excavations, just like in the United States. So in this case, when you have a really deep excavation, you need to account for the condition for the embedding of the wall, you know. How do you account that in your analysis? Because I think that you have this floating wall, and you develop everything based on this floating wall condition. How your results are going to change if you account for the length of the leg of the wall and things like that?
You're talking about piles?
I'm talking about the retaining wall. I mean, we usually use piles combined with truss to make a flexible wall when we are working on excavation. Here, you know, you are plotting like a typical retaining wall for like a road or something. But in practice, you have actually piles and that are connected to a beam and that make the.
So I'll go back to the schematic here.
There you go.
So, yes, if you have piles, they would be down here, right? So the piles would be part of the foundation system supporting the wall and the base slab here. And in this context of an inertial soil structure interaction analysis, it's actually pretty simple. The piles would be what governs the properties of these springs and dashpots. So they would just become a lot stiffer than if it's shallow only.
But if the piles are part of the retaining wall, you know, like it usually is in practice, because you put some piles and then you connect everything with truss.
So if
and
this goes down, you're saying?
Yeah, that's right.
Yeah.
So that wasn't accounted for in the method, I think.
It's only accounted for through the stiffness of the foundation.
Okay, so
So
basically,
we don't have continuity of the bending stiffness
this is
from the
more
wall.
this is more or less a wish in place kind of solution, right? I mean, if you have, for instance, a construction site and you're excavating, and then you have an earthquake, but you want to design for these air pressures, this method will work, or what would
No,
you
it would
need to
work.
do?
So let's take the case you described. So let's suppose you start by installing piles, and then maybe you put a wall in front of those piles. That's what you see on the interior of the excavation here. So you have a combination of a wall with the piles right behind it there. So you still have the free field doing whatever it wants to do. That's unaffected. You have the hybrid of the two elements here, which would need to be taken into account in the flexural stiffness, obviously. Then you have a pretty significant axial stiffness, and you have some rotational stiffness associated with this pile here. Okay, so that's within the context of this problem, that's where it comes in. It would influence the EI, and it would influence the stiffness elements that are below it. And there would be actual continuity in the case you described, not for the wall surface, the facing surface, but for the piles behind. And so that would have an effect, but our analyses have shown that when this part up here is flexible, so beta H more than 0.5, when this part is flexible, that flexibility has more influence than whatever it is you're doing down here. Not that this doesn't have an impact, it does. It definitely has an impact. The more flexible the foundation support is, the more the whole system can conform with the free field motions and the pressures go down. The stiffer it is, the opposite is the case, the pressures go up. So I don't mean to say it doesn't matter. It does matter. And for the case of a very stiff foundation support, it would drive up the pressures. The way that our solution was worked out, this is fixed. So if you go to the extra effort to model the flexibility, including piles, whatever, compared to the simple solution that I've shown, you're going to lower the pressures. So again, that was deliberate because we were aiming to have something simple that would be a little conservative, and by doing more work by the engineer, you will be rewarded for that extra work by lowering your pressures. Yeah.
Well, is there any other question? ¿Alguna otra pregunta? Yes, please.
Hi, Professor. Thank you for your presentation.
You're welcome.
At the end, you showed us the residual between some cases and your model. And I think UC Davis was a bit underestimated. And
So you're talking about the validation?
yeah.
A little ways to go here. Okay, maybe this one?
Yes. I think the UC Davis was a little bit underestimated. The red triangles.
That would be Boulder, actually, but I think your question still applies, right?
Right, Boulder. And did you find a reason for this? Maybe for PGA values or some flexibility?
Yeah, so it's a fair question. So there's 2 points I would make, and I'm glad you raised the issue of these Boulder tests. The first point is, why is it that this set of results, the red symbols, are so much more scattered than the blue ones and the green ones? Which is not actually your question, but it's related, I think. So that was not immediately obvious to us why that should be. We, as I mentioned, Shade Ashti was someone that we were talking to and working with at different times on this. And she was not surprised when she saw the scatter. She attributes it to essentially experimental error due to noisy strain gauges. And so that there's a not inconsiderable amount of uncertainty in the measured values. So the level of resolution in the Davis test, because it's a much larger centrifuge, it's easier to get these sensors in there. You can use larger ones, is better. And of course, in the green symbols, there's no uncertainty. It's a simulation result. So for the uncertainty in the red symbols, our best answer to that is it's an experimental data scatter due to these strain gauges that measured the curvature. The question you actually asked was, why is it that the red symbols, if you average them, are less than 0? Right? And the same is true, well, not necessarily. The same is actually true of the Berkeley Davis test, but not to the same degree. So the reason that these things are negative is because of simplifying assumptions we made in formulating the method. One of the ones was the rigid base assumption. Another one was the lack of consideration of the heterogeneity of the soil. So a few things like that force our pressures up a bit from what they would otherwise be. So it would be better to be unbiased, but the thing, there's solutions that we engineers produce that are really meant to be unbiased. When we do a complete analysis, a thorough analysis, if we're making a ground motion model, like I was talking about yesterday, we want no bias. There are other times we make models that it's actually good, at least in my opinion, to have bias. These are when you simplify a more complicated problem to a simpler one so that you can get an answer quickly. And if you're going to take a shortcut, there should be a penalty. You should be conservative. You should be having thicker walls and things like that. You should never have a simplified method that is unconservative. Okay? Which is not, of all the different problems with mononoble Yokabi, that is not one of them. It is not unconservative. It's too conservative. But we wanted to be a little bit conservative. And so as we made some of these assumptions, we were hoping it would turn out this way, basically. So that's why it is. It's because these certain things that do actually influence relative displacement are not accounted for in the model.
Thank you.
Well, thank you very much, John. We want to thank you for you coming to Mexico to give this very nice lecture and to yesterday's lecture as well. We want to give you and Victor, please could you come here, Victor, a present just to show you how happy we are that you were here, and we're hoping you to come
Coming in, yeah.
more often.
Thank you.
So we're hoping that it's going to fit you, you know, like, yeah, otherwise we can go to the store right now and change it.
I know what to do with this. I am pretty hard.
Try let's see if this fits you.
Let's try. We can take pictures. Did you get Victor a small one?
Saying that I'm happy that we were able to, a little bit short.
A little bit, sure.
For some reason.
What do you think? Oh, okay.
There was a mistake that
Really? You found this the bigger one? Let's try. Yeah, a lot of clothes don't fit me very well. Problem with being tall. This is bigger. Yeah. Thank you. You were a great audience. Appreciate the questions.
Now we can go to the rectoría and take some pictures.
All right. Have a copy.
Muchas gracias por resistencia a cualquier tema. Vamos a, Leo, you were able to come. That was nice.
If you want to visit the station,
Can we do it on the